In lesson 12.3, we're still going to talk about sequences and series, only this time we are going to focus on geometric sequences and series. A geometric sequence, this is where consecutive terms have a common ratio. So to get from one term to the next term, we use multiplication. With the arithmetic sequences, you saw how we were adding that common difference each time. This time we're looking for a common ratio. So if we look at these two examples, we can see that to get from the 1 to the 2, we're multiplying by 2, so times 2. To get from the 2 to the 4, we're multiplying by 2. From 4 to 8, times 2, times 2, times 2. So that means our ratio is that 2, because we're multiplying by 2 to get to the next term. This next example, you can see that the numbers are going down. Well, in an arithmetic sequence, when the numbers decreased, that meant we were adding a negative number. It'd be really easy to look at this and say, to get from the 81 to the 27, we're dividing by 3. And if you look at the pattern, 27 divided by 3 is 9, divided by 3 is 3, divided by 3 is 1, so that divided by 3 definitely is getting us where we need. The only thing that's going to be tricky about a geometric sequence is your ratio has to be written in terms of multiplication. So if you say that r equals 3, well, that means that we would take 81 times 3 to get the next term, which is not what's happening. So instead of divided by 3, we're going to say multiply by 1/3. 27 times 1/3 is 9, times 1/3 is 3, times 1/3 is 1, times 1/3 is 1/3. So in a geometric sequence, if your numbers are decreasing, your ratio will be a fraction less than 1. If you need to tell whether or not a sequence is geometric, sometimes you can just tell by looking, but if you had to show someone, what's the work that you show? So what you can do, because geometric sequences involve multiplication, we're going to do the opposite of that with division. We're going to set up ratios and see if we can find a common ratio. So to do this, we would take the second term and divide it by the first term. And between the 1 and the 2, that has a ratio of 2. Then we would take the third term and divide it by the second term. And if this was geometric, we'll get the same answer, so there's a common ratio. But we can see we're getting a 3. So far I would say this is not geometric, but let's just look at it a little bit further. If we take the 24 and divide it by the term before it, which is 6, we get 4. So we are getting a ratio of 2, a ratio of 3, a ratio of 4. Because those are all different numbers, that means that this is not geometric. If we follow the same thinking with our second sequence down here, check to see if it's geometric, but what's the work you show? Take the 8 divided by -4, and we get a -2. Now take the -16 and divide by 8, and look at that, we get another -2. So these -2s, these are the ratios so far. 32 divided by -16, oh, there's -2. Then you might as well just keep going through the whole thing just in case they throw you a little curveball at the very end of your sequence. But they didn't this time, and you can see all of those ratios are the same, so that's a common ratio. So your ratio is -2, which means, because it was common, this is a geometric sequence. When you are working with a geometric sequence, we're going to write the rules two different ways. First is the explicit rule. This is what you'll do more of in this lesson. The rule looks like you have your a sub n, and that's just the start of your rule. And then the two things you need in order to write a geometric rule is the first term, so you take a1 and you multiply it by the ratio raised to the n minus 1 power. So as long as you have a1 and your common ratio, then you have enough information to write the rule for a geometric sequence. Another way to write a rule is the recursive version. So recursive rules, you've been introduced to that a little bit. If you're writing a recursive rule, there's always two parts. First part is you have to have a starting point. Because in recursive rules, each term is built on the term before it, you are going to need to tell people where to start. They have to have a starting term. So a1 is the first term, and then the rule, an, if you remember this a sub n minus 1, we have talked about that as being the previous term. So if we take the previous term and multiply it by our ratio, that will get us to the next term. And that's how we'll write a recursive rule. So I think you guys are actually going to like writing rules for geometric sequences. They're pretty straightforward, and there's not a lot that you can do in terms of simplifying. So if you're given a sequence, and in this case they even told us that it's geometric, so that took that piece out of it. We know it's geometric, so the rule has to follow this, where you have your first term times your ratio raised to the n minus 1 power. So if they're actually giving you the sequence, that's wonderful, because you know then what your first term is. It's just that first term. And the common ratio, so we just look at the sequence to figure out what are we multiplying by to get to the next term. And just by looking at that, we can see that we're multiplying by a 5. So our sequence, the rule for the sequence is just going to be an equals first term 3 times your ratio raised to the n minus 1 power. And that actually is all that you can do. You can't do any simplifying beyond that. It's tempting to want to multiply the 3 times the 15, but if we keep in mind how the order of operations works, you would take this base of 5 and you'd have to first raise it to this exponent before you can do this multiplication. And since this exponent still has that variable in it, it's going to stay as that n minus 1. So I can't simplify this, which means I can't multiply this yet. So that's how we leave a rule for a geometric sequence. If you're given both a1 and r, then you just basically plug them in and you're done. So there's 3 versions of kind of what you'll be given when you write a rule for a geometric sequence. The last slide showed the first one, if you're given a1 and r. In this case, you're given the common ratio, and you know that the fifth term is 3. So that means a sub 5 equals 3. So what we're going to do is we can use the setup of the rule to help us find that first term. We can plug in what we know and solve for what we're missing. So I'll start over here. First, a1, we don't know what it is. The ratio we know is a -1. And what we're going to be able to do is plug something in for the n and for the a sub n based on this term. This came up in the arithmetic sequence where this subscript is always what goes in for n. So I know that if I go back to the rule, this is going to be a 5 minus 1. And then what's it going to equal over here? Well, if you plug a 5 in for n, that means you're finding the fifth term. And we can see over here that the fifth term is a 3. So we're going to put a 3 right here. And that just gives us a nice little equation to solve for a1. So if we keep solving, you'll have a1 times -1 raised to the 4th power. And then -1 to the 4th power ends up being a +1. And so if we keep going, we can see that a1 is 3. We have a1, we have our common ratio, so we are good to write this rule. Our final answer will just be an equals the first term of 3 times the common ratio, -1, raised to the n minus 1 power. Done. So here's the problem that will be the most work if you're not given your common ratio and you're also not given the first term. When I see problems like this, I kind of like to think about what's happening a little bit and see if we can logistically work our way through it. So here's the 4th term, and we know that it's an 8. And here's our 7th term that we know is a 1. So if we think about how do geometric sequences work, to get from one term to the next term, we're multiplying by our ratio. And to get from this term to this term, you're multiplying by your ratio. And to get from here to here, you're multiplying by your ratio. So what we actually have going on is if you start with this 8, and if you multiply by the ratio, multiply by r, it will get us to that 1. So the equation we can say 8 times r times r times r will get us 1, so it equals 1. And just to clean this up a little bit, 8r cubed equals 1, and now we just have a nice equation to solve for r. We would divide both sides by 8. R cubed equals 1/8, and then do you remember how to undo an r cubed back from, I don't know, chapter 6? Cube root both sides, so that leaves you with r equal to, now the cube root of 1 over the cube root of 1 over the cube root of 8, well, I just kind of said it, you can break that up. And again, I'm showing every single step here, but the cube root of 1 is 1, cube root of 8 is 2. So we're getting a ratio of 1/2. So I could keep going with the problem, but you're going to watch a video on this anyway. So once you have your ratio, the only thing you need now is your first term, and then you can write the rule. So check out the other video definitely to see how this problem gets finished up, or one like this. So now we're moving on to a geometric series. In 12.3 we talk about a finite geometric series. That means that it has a finite number of terms. You know, maybe we're adding up the first 10 terms of a series. In 12.4 you deal with infinite geometric series, so that's kind of where that distinction is made. And once we get to 12.4 it'll make more sense. So to find the sum of a geometric series, we have a sum formula right here where you can see we have A1, which we already know is the first term. You also have R, which is the ratio. And then the N is the number of terms in the series that you are adding up. And really we're avoiding adding them up by hand by using this formula right here. Alright, here's our last slide, and I'm really hoping that this has been shorter than the 12.2 intro video, which I think broke the record for the longest. So if we have to find the sum of the finite geometric series, you can see, you guys have seen this notation a little bit already. You would start by plugging in a 1 and stop with a 10 and add all the numbers together. Well, that's kind of a lot to do by hand, so that's why we get to use that formula where the sum equals A1 times 1 minus r to the n over 1 minus r. Let's see if I can erase it. There we go. So let's just identify what we have. We need A1, we need r, and we need n. A1, if you see, here's our rule right here next to our sigma notation, and that just follows right in order of what a geometric rule looks like. This is always r, that's raised to the n minus 1 power, and then, oops, that's always the A1 in front of it. So it kind of lines up quite nicely for us where we can see that A1 is 1/2, r is 6, and n, number of terms. Well, if you start by plugging in a 1 and you stop when you plug in a 10, that means that n will equal 10. And it doesn't equal 10 every single time that you have a 10 up here. You really do have to pay attention to the bottom number also to see where do we start. Because if we started with 5 and went up to 10, that wouldn't be 10 terms. Alright, so from here it's just a matter of plugging in and simplifying, and I'll just start it out. The 1/2 goes out front, raised to the 1 minus 6 to the 10th power over 1 minus 6. And so you just follow your order of operations and working through that, do your exponent, subtract these, then divide, then multiply by 1/2. But there's a video that goes through all of those pieces, so I don't need to do it right now. And that's 12.3.